Let's begin with a puzzle. What do the numbers -1 and 4 have in common? They're not lucky numbers or secret codes, but they do hold a secret. If you plug them into the polynomial p of x equals x squared minus 3x minus 4, something amazing happens. Try x equals -1, p of -1 equals -1 squared minus 3 times -1 minus 4. That's 1 plus 3 minus 4 equals to 0. Now try x is 4, p of 4 equals 4 squared minus 3 times 4 minus 4. That's 16 minus 12 minus 4 equals to 0. In both cases, the result is 0. These numbers are called the zeros of the polynomial. But here's a twist. What do these zeros look like on a graph? A zero of a polynomial is a value of x for which p of x equals 0. But geometrically, it's where the graph of the polynomial intersects the x-axis. Let's visualize this. Take the graph of y equals x squared minus 3x minus 4. It's a curve, a U-shaped one called a parabola. Now notice something. This curve touches the x-axis at exactly 2 points where x is -1 and x is 4. These are the x-coordinates where the value of the polynomial becomes 0. So, the zeros of a polynomial are nothing but the points where the graph crosses the x-axis. Now let's explore what can happen with quadratic polynomials graphically. We've already seen a case where the graph cuts the x-axis at 2 distinct points. That means 2 distinct real zeros. But what if it touches the x-axis at just 1 point? That means there is only 1 zero and it is repeated. We call it a double root. And finally, what if the graph doesn't touch the x-axis at all? In that case, the polynomial has no real zeros. It means p of x never equals 0 for any real value of x. So, depending on how the parabola sits, a quadratic polynomial can have 2 distinct zeros, 1 repeated zero, or no real zero at all. So, why should we care about these zeros and their graphs? Let's say you're designing a bridge. The height of the arch is defined by a quadratic polynomial. The points where the bridge touches the ground? Those are your zeros. Or imagine a football kicked into the air. The ball's path follows a parabolic curve. Where it lands? That's one of the zeros of the polynomial representing its motion. From sports to structures, zeros show us real-world contact points. Let's solve an example and connect the algebra to the graph. Take this polynomial p of x equals to x squared minus 2 times x minus 8. Step 1. Factor the polynomial. We find 2 numbers that multiply to -8 and add to -2. Those are -4 and 2. So we write p of x equals to x minus 4 times x plus 2. Step 2. Find the zeros, set each factor to 0. X minus 4 is 0, so x equals to 4. X plus 2 is 0, so x equals to -2. So, the zeros are x equals -2 and x equals 4. Step 3. Visualize it. On the graph of y equals x squared minus 2 times x minus 8. The curve will intersect the x-axis at x equals -2 and x equals 4. Those are the points where the polynomial becomes 0. What about cubic polynomials? Take the polynomial p of x equals x cubed minus 4x. Try plugging in values. P of -2 equals to 0. P of 0 equals to 0. And p of 2 also equals to 0. Graph it and what do you see? The curve crosses the x-axis at these 3 points -2, 0 and 2. That's the beauty of cubic polynomials. They can have up to 3 real zeros. To sum it up, the zeros of a polynomial are where its graph meets the x-axis. In quadratic graphs, that means up to 2 real zeros. In cubics, up to 3. In our next video, we'll connect these zeros to the coefficients of the polynomial. Algebra meets symmetry. Till then, stay curious and keep plotting.